My name is Michał Wrona, and the goal of this talk is to present the paper on the relational width of first-order expansions of liberal finitely bounded homogeneous binary cores with bounded strict width. I'm from Kraków, Poland, from Jagiellonian University. So the whole thing is about constraint satisfaction problems over infinite structures. These structures have bounded relational width, and the main result is a characterization of relational width of some of structure of interest. We conclude with open questions. So the constraint satisfaction problem for us is parameterized by a relational structure over a finite signature, but not necessarily finite domain. An instance is a set of constraints, each of which consists of variables and a relation. The length of the tuple of variables matches the arity of the relation. And we ask if there is a solution, which is an assignment to variables so that each tuple of variables lands in the corresponding relation. There are many problems, computational natural problems, that can be expressed by choosing the appropriate structure A. So K coloring is CSP for the structure K with K integers and inequality. We can easily model KSAT by using appropriate constraints to model clauses, and we can also express solving equations over finite fields. Until recently, the main open problem was to confirm the Federer-Vardy conjecture, saying that every finite structure, for every finite structure, either the problem CSPA is in P or it's NP complete. So the class of constraint satisfaction problems over finite structures omits NP intermediate problems. And it was proved independently by Andrei Bulatov and Dmitry Zhuk 3 years ago. There are two different proofs, but they both use so-called algebraic approach and both confirm algebraic dichotomic conjecture. Meantime, we learned that we can use similar tools, algebraic tools, to speak about the complexity of constraint satisfaction problems over some infinite structures. So these infinite structures in these presentations are first-order reducts of countably infinite finitely bounded homogeneous structures. So structures which have first-order definitions in these finitely bounded homogeneous structures. So for instance, Q with the order is homogeneous. It means that every local isomorphism between finite substructures can be extended to an automorphism, and it's finitely bounded, which means that there are several finitely many bounds. In the case of Q with the order is the loop, the symmetric edge, the independent set, and the three-element cycle. So a finite structure can be embedded into Q with the order if and only if none of these four structures embeds to this finite structure. So CSP for Q with the order also is the problem that cannot, it's digraph acyclicity, and this is a problem that cannot be expressed as constraint satisfaction problems for finite structures. So this formalism is richer. You can also use it to express some problems in scheduling and temporal and spatial reasoning. Other examples are random graph. So where the forbidden substructures are the loop and the directed edge. Random graph is a universal graph, and every countable graph can be embedded into it. You have also hands-on digraphs, so it happens that for every countable set of tournaments, there exists a digraph, hands-on digraph, such that it omits exactly these tournaments. And if there are finitely many of them, then the hands-on digraph is finitely bounded. And then we go to first order reducts of finitely bounded homogeneous structures. So here we have a reduct of Q with the order, we have the relation R, and this is a ternary relation, so we have triples x, y, z, such that x is greater than y, and x is greater than z, or x is greater than z. And all these finitely bounded homogeneous structures over finite signatures are omega categorical, which means that either although the relations have infinitely many tuples, there are also always finitely many orbits of tuples with respect to the automorphism group. When we go to an instance of CSPQR, we can give the following example. We have first constraint saying that x1 is greater than x2 or x1 is greater than x3, and the second constraint saying that x2 has to be greater than x1 or x3. This instance has a solution, like sending x1 to -1, x2 to -2, and x3 to -3 does the job. Indeed, -1 is greater than -2 and -2 is greater than -3, but when we add another constraint saying that x3 cannot be the smallest, when we cannot choose the smallest value, right, for any constraint, so these three constraints displayed here are not satisfied. And for this class of constraints, we have an algebraic theorem saying that either this redact interprets +1 in 3SAT, and in this case the problem's NP complete, or the structure there's an operation called pseudo-Siggers operation that preserves the structure. Pseudo-Siggers means that there are unary E1, E2, and 6 RF, so that the displayed equation is satisfied. And the conjecture is that in the second case, the problem is in P, structurable. And a similar conjecture is conferred for finite structure in the proofs by Bulatov and Zhuk. So basically one can think of two ways of proving it. The first one, which worked in similar cases, is to reduce this problem to the dichotomy for finite structures, and it can be sometimes done, for instance when the pseudo-Siggers operation is so-called canonical, but it's also known that there are some problems tractable in P which don't have canonical pseudo-Siggers operations. So it seems that we need to develop an algorithmic technique which works always for redux of finitely bound homogeneous structure preserved by pseudo-Siggers operation. So to this end, it seems it's important to understand the existing techniques. Similarly, as in the finite case, for these infinite structures we can use local consistency sometimes. Structures whose CSP can be solved by local consistency are said to have bounded width, or equivalently they have bounded relational width, but then we use minimality instead, algorithm establishing minimality instead of consistency, but these are exactly the same structures. So we'll look at the structure with the domain Q with two relations, the order and equality, and with the following constraints: x1 has to be less than x2, x2 has to be equal to x3, and x3 has to be less than x4. x4 has to be less than x5, and x1 equal to x5. And we established two-free minimality. So first we add constraints so that every three-element subset of variables was covered by some constraint, so that it was in the scope of some constraint. And then we remove tuples. And this free here, like we added constraints with the scope of three variables, is this free from two-free minimality. And then we remove tuples in order to obtain constraint when agree on projections to the same two variables. And this two is this two free into free minimality. So we added these constraints, and now we remove tuples. So we look at the constraint C1 to 3, and we have the scope x1, x2, x3, and the relation consisting of triples d1, d2, d3. And we started with q to the third, but we can remove some tuples, right? Because we want the projections to agree, so we have that d1 less than d2 because of the first constraint, d2 equals d3 because of the second constraint, and in consequence we have d1 less than d3. Then we have C351. We look at this relation and this constraint and the relations d4, d5, d1. So that d4 is less than d5. It comes from the constraint c4. d5 equals d1. It comes from the constraint c5. And in consequence, we have d4 less than d1. Finally, we look at c3, 4. Of course, the algorithm works for all the constraints, and we present only some of them just to see something. Okay, so this c3, 4 has this relation of triples d1, d3, d4 such that d1 is less than d3, and it's because of the constraint c1 to 3. d3 is less than d4. It's because of the constraint c3, and d4 has to be less than d1, and this is because of the constraint c451. But it's not impossible, right? Because here we have this three-element cycle which is forbidden. So basically this relation is empty. And since we only were removing tuples which cannot be a part of the global solution, we can conclude that the original set of constraints has no solution. Of course, we can replace 2 3 with any k else such that k is less than or equal to L and establish KL minimality. So we obtain an equivalent instance such that for every element subset there is a constraint whose scope contains the subset of variables, and we remove tuples so that the projection to k element subsets equal It's known that if KL are fixed, then we can do the whole process in polynomial time. L is in the exponent. So, and if we end up with an empty constraint, then both set of constraints have no solutions. But sometimes we have if and only if, meaning that if the whole process doesn't end up with an empty constraint, then we conclude that the original constraint set of constraints has a solution. And such structures have relational with KL if we establish KL minimality, and have bounded relational with if there exists KL such that they have relational with KL. And it's known that for finite domains, if this relational width is finite, then it is 1, 1, or it's not 1, 1, and then it's 2, 3. So we can ask what is the relational width of reducts of finitely bounded homogeneous structures. But before we will try to answer this question, we'll look at what we can say about bounded width first for finite structures. So it's very well understood. There's a theorem by Barto and Kolik, and many equivalent conditions, algebraic conditions. Just to mention one, structure has bounded relational width if and only if it's preserved by two weakening unanimity operations, F and G, so that the displayed equation is satisfied. And actually, at the top of this, Libor Barto obtained his characterization. So first, perhaps we should ask if there is a set of identities characterizing bounded relational width over reducts of finitely bounded homogeneous structures. And it was open for some time, but it's known since recently, and it's presented at this conference, this result, that there is no set of identities. And this is one of the reasons why we proved something a bit different. So our theorem is for a bit stronger condition, for bounded strict width, not relational width. So we prove that, so we start with the structure A is some kind of finitely bounded homogeneous structure called liberal finitely bounded homogeneous binary core, explained in a while. When we go to its first order expansion, so Redact, which contains all relations from A, it is B, and this B is required to have bounded strict width, defined in a while. Then we prove that B has relational width to LA, and LA is the size of the largest band for A. But LA is at least 3. So if, for instance, the structure A is a Hanson digraph forbidding like graphs over like tournaments over 7 elements but not more elements, then we have relational width to 7. And binary core is just a relation, finitely bounded homogeneous structure, such that we have equality and we have anti-reflexive relation, so that for any pair of elements in the domain, there is exactly one anti-reflexive relation that contains the pair AB. A is liberal if it doesn't forbid substructures of size 3, 4, 5, and 6. Structure has bounded strict width if establishing KL minimality for some KL not only decides if there is a solution, this is what we require for bounded relational width, but we have more, but we require more. Every partial solution of this minimal instance is extendable to a total solution. And for instance, the structure behind the problem to SAT which is of course also CSP problem, or the structure Q with the order, so the diagram isoclassicity problem may have this bounded strict width property. And special cases, when we take A, which is a random graph, we remember that all the forbidden substructures are very small, like of size 2. And we see this random graph over the signature when we have equality, edge, and non-edge. E and N are anti-reflexive, and we go to the first order expansion B of A with bounded strict width, then we know that B has relational width to 3. And as I already said, if we take A, which is finitely bounded Hanson digraph seen over this extended signature, so that it was the binary core as defined above. So we have the arc, the non-edge relation, and equality, and forbidding tournaments of size 7 only. Then if we go to the first order expansion with bounded strict width, but it has relational width to 7. We can also rewrite our result in terms of polymorphism, because there is this characterization of the bounded strict width over omega catholica structure. So it's known that a structure has bounded strict width if and only if it's preserved by an oligopotent quasi near unanimity operation, which means that the diagonal, this fxx, preserves all reducts, and that f satisfies the displayed equation. In the first term, y is in the first coordinate, in the second coordinate, in the last but one in the last coordinate, and finally we have x, 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 x. So we can rewrite our main theorem. So A is liberal finitely bounded homogeneous binary core. B is a first order expansion of A preserved by an oligopotent quasi near unanimity operation. Then B has relational width to LA, where LA is the size of the largest band for A, but not smaller than 3. And we can also ask if the developed methods can be used to prove some more results of the form let B be preserved by an operation satisfying the set of equations E when something happens. Of course, we have some more requirements here, like liberal binary core, first order expansions, but the whole proof is basically very much based on this very general assumption that we have only a polymorphism, and this is what we need to solve the tractability conjecture, right? So for instance, so we need to develop some methods that can be used then to show that certain CSPs are in P. And so we are also interested in completing our characterization. So we have the following conjecture: let A be a finitely bounded homogeneous structure and be a first order expansion of A, preserved by an oligopotent quasi unanimity operation, or equivalently with bounded strict width. Then B has relational width KA-LA, where Ka is the largest arity of relations in A. We had 2 in binary cores, and La is the size of the largest band for A, but this is at least 3. So it certainly matches this result I'm talking about for first order expansions of liberal finitely bounded homogeneous binary cores, but also our previous paper on first order expansions of homogeneous graphs from Stacks 2020. Okay, thank you for your attention.